online optimization. Today we basically will stop at here, basic stuff. So I'm going to minimize a variable x. X is called a vector because I write bold inside a set. Let me call it big X. Okay, that means X has a constraint subject to a function. Let me call it, let's say H. H is a function that takes two things. One is the variable X, that means this X. And then there is a random variable. I write it like this. This is the random part. So all the Greek letters are always a random variable. And then X, Y, Z, alpha, lambda are like scalar or parameter. So these three are random variable. Alpha, beta, gamma, delta are like parameter. Okay. And then X, Y, Z, A, B, C are like scalar. Notation is very simple. This is set. So this is variable. This is matrix. This is set. Or these are the sets. And then this X is big set, right? So now it's a subset of something. We focus on d-dimensional space or n-dimensional space or whatever space. So this is like you have a vector with d number. So we basically want to minimize something like this, and then this is not doable because this is a random variable. So we have another f outside of it. Okay, this is basically the setup. So that means you want to have something related to random, and you can control. And then you say I want to minimize the f of this thing. One example of this is the expected value. That means on average, what you should do on x to make the average of h small, something like that. But in general, it does not really need to be an expectation, so it will be another function f. Okay, so therefore we have so many symbol. Okay, so now let's talk about symbol. You have s, d, x, y is just set. Okay, and then there are classical notation: a real number, positive number, natural number, and this is now important. For example, I want to write 1, 2, 3. Lazy notation is I just write 3. Okay, this means 1, 2, 3. And this will be useful because I always have a t round, so blah 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 blah, blah t. Then I just write this t. Okay. And then now scalar is just lowercase, okay, a, b, c, d, okay. And then vector are bold case, and then usually rd or rn or whatever thing. And then because the issue is we have a sequence, so we have a x1, this is vector, x2 is a vector, so we have a bunch of vector until xt. Then if I want to talk about the ith component of this, I cannot put another one here, it will be very confusing, so I have to write a square bracket here. Okay, let's say like this. Okay, this is inner product. Okay, so okay, with this notation, then just sum each of them. And so this is the notation. This means the vector at time 3, the fourth component. Okay, and lastly, Greek letter is always random variable. So following the style, this is scalar random variable, this is random vector. Of course, we can have random matrix and then whatever random set. Okay, vector. So these are vector, and I have t of them, and inner product. And then L2 norm is just inner product. So again, this means transpose. Okay, and then Cauchy-Schwarz. Okay, you have this. And then these are classic. And then we also have L1 norm. L1 norm means everybody take absolute value, and then some of them. And then L infinity norm, that means the largest entry in a vector. So very quick overview, you have a coordinate system, 2D. Let's say this is a vector x. Then L2 norm is how big is this circle. So if I have this box, then this one is longer. Largest entry is the y-axis. So therefore L infinity norm is. L1 norm is how long is this one plus how long is this one. L2 norm is how long is this one. Okay, so that's it. And then in the same sense, if you replace these two by 1 and infinity, you have another Cauchy-Schwarz. This is just other Cauchy-Schwarz. Lastly, you have the dual and this one. I will come back to this when we talk about conjugate. We will use this later. And then now another thing, we have statistics because we have random stuff. So what are the random stuff? You have random vector or random scalar. And then we will have distribution d. So this means what? This means this random variable take a distribution d. To make everything simple, always a normal distribution, let's say. So it's a mu sigma or mu sigma. Okay. So basically means what? Gaussian distribution. So one-dimensional Gaussian distribution is you have something like this. Okay. And on average is a mu. And then this gap or the width is a sigma. Okay. And then there are something like 2 sigma, 3 sigma means very rare event. Okay. So something like that. And then, but generally, we can write d. D can be any distribution. For example, if it's flipping a coin, then this is a balloonie. But anyway, and then for random variable, we have something like e and v. Because of time, we don't touch anything on v. Okay, no time to talk about v. We just talk about e. Okay, so what's the e? E is the expected value. So suppose I have this. Okay, then what? Well, looking at this particular curve, what's the average? Well, approximately this line, right? Then this is the ex, this is x, okay, and this is time. what is v? V is like how much this fluctuate, right? So this is a Vx, okay, something like that. Then Ex is basically the expected value of a random variable. The full notation will be the distribution we write down, but usually lazy, don't write anything, just write E, okay? Now another thing, suppose I have a random variable h, f5, and then h is a function taking the random variable, so this is also a random variable. So for example, suppose this is a normal distribution 0, 1, that means 0, 1, that means something like this, right? Then suppose I have a function of this, it's just this plus 1. Then I just basically move this one unit upward, right? It's still random variable, right? So therefore, if this guy is a random variable, then you do something on a random variable is still a random variable. So therefore, we can also say E of h of phi is also a random variable. And similarly, we can write the full expression, but I'm lazy, so I don't write that, okay? And then now function. So we are going to talk about function. So abstract function, that means what? I have a set S, okay, S, so we have a space, whatever S, and then every point here under a function f will give you a number. Let's say this is 1, let's say this is a 2, and then let's say this is a 3. It's possible something mapped to the same number, right? The only rule of function is you cannot have a point go to two value, right? But it does not matter. You have multiple points go to the same value, right? So this is like a function. And then what? We have the following condition called Lipschitzness. What the heck is this? Okay, the definition is I have a S to R. S is such whatever thing. And then this U and V are function f of U and f of V. Because f is defined in S, so therefore U, V are by default should be inside this set, okay? So for all the U, V inside the set S, the distance between them this is before applying the f, right? This is after applying f, right? So suppose I have a point here, this is U, and this here is V. So what the heck is this thing? This thing is exactly U minus V distance, right? And then because I have a function f, map everything to a real line, that means this guy can go to here. Okay, let's say this guy go to here. Okay, then now this is what the heck is it? This is fu minus fv, right? So the ratio between my length of green and the other green, this two is length, right? I can divide them. This thing is the same as fu minus fv divided by u minus v, right? Small l, right? So this is a ratio of length smaller than l. What does it mean? It means this length grow bigger cannot be bigger than L. The ratio cannot be bigger than L. So suppose this is 1 cm, okay, 1 cm, and this is 10 cm. This L means what? That means if I have a 1 cm become 10 cm, that means I grow 10 times. But L means how much can you do that for any UV? There is a maximum ratio. This is the first way you can see this. Or the second way to see this is you don't care about this picture anymore. Now, what I'm going to do is I define my U is V plus small change, so V plus small change. And then now what's the thing here? Okay, I make a mistake, this should be V anyway. So I will have U minus V, but U is V plus H, so this thing is V plus H. The V and V kill each other, so I have this. What the heck is this? This looks like derivative, right? So therefore, this also means F cannot change too fast. Because this looks like derivative, so if I have this, what does it mean? It means derivative cannot be too big. So if derivative cannot be too big, what does it mean? You have a function, this is a function, right? This is a function, right? Derivative is too big, is like you have this thing or you have this thing, right? You have 90 degree. What does 90 degree mean? You suddenly jump value, super fast change. So if I have this Lipschitz condition, basically mean you cannot have super fast change. This is the intuition. Now I have another thing, gradient and Hessian. What the heck? So I have d-dimensional vector. So I have f, x is a vector. So this is the lazy form. What's the full form? x1, x2, x3, x, xd. Okay. Now each of them I can take a derivative on xi. For example, x1. What does it mean? What's the change of this whole thing on this guy? If I draw two-dimensional space, so I have just x1, x2. So x1, x2. If I only have this, what does it mean? It means I don't care about this direction. I just care about this direction, how much it changed. And if I have x2, that means I only care about how this changed. So if I stack all of them, it means I care about how this changed and also how this changed. Then it gives me complete information of the gradient. And I stack everything together. That means how each of the component is changing. This is a vector. This is a scalar. This is a vector. Now, if I do the same thing again, so I put another gradient here, then I will have 2. Now, this means what? This thing, how does it change in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Then I have grow another vector in this direction. Okay? So, the first guy will be this guy, dxy. So, therefore, 2 times. What's the second guy? Second guy is this particular box, ddx2. So I have a second guy here. And then third guy, fourth guy, second guy, so on. So in the end, this will be also d-dimensional vector. And I can do for each of them. So I have d-dimensional vector, d-dimensional vector, d-dimensional vector, blah, blah, blah. I have a matrix. So second order derivative is a matrix. Okay? And in the same sense, you can have third order. That means you derivative again. Then you have another d-dimension in the 3D sense. But we don't care. Okay? So in a general way, you can d until everything explorable anyway. So this is the gradient. This is the Hessian. We most of the time we will just talk about gradient. Sometimes Hessian is very useful because I can use Hessian to deduce gradient or use gradient to deduce Hessian. So this is the gradient. Now these are done. Now we go to some special function. So these are called special function. It's about constraint. So let me come back to here. We are talking about a function from S to R. So that means what? That means I care about a set S, and I say everything in this set S, this is R, is somehow go to here. Okay, I have F. Here's the thing. What happens if I have a point here? If I have a point here, this point, let me call it X, not inside S. Then the question will be, okay, how do I go to here? Well, in this kind of situation, we always say there is an infinity. Everything outside set S go to infinity. That's the idea. So the idea is, if I have a region S, I can think of this as a constraint. That is, in some optimization problem, suppose you want to minimize, due to some reason, you want to minimize x squared, and you want x larger than 0. So if x is -5, you are unhappy because x cannot be negative. You are saying, I only allow x to be positive number or 0. I do not allow this. So in this particular case, S is real number larger than 0. Then what happens if you have a -5? Then you are saying, now, this is your f, right? This is your f, right? Now you're saying, no, for this particular case, f on this guy go to infinity. So it is saying us x squared normally is like this, right? It's f equal x squared, right? But now you're saying I can allow only positive part. Yellow, okay. Red, not okay. Red is illegal. So what to do? Then what are you going to do is that this part is wrong because this means red region, I get some number, right? I get some number, right? But now I'm saying, no, I don't want this. So what I'm going to say is, okay, here is positive infinity. So everything red have to go to positive infinity. So I have to change this particular line. So what I'm going to do is, I no longer have red line, I have my green line. You can imagine this is green line. So it's a super fast function and it immediately go to touch infinity. And the true picture is, at this moment, it directly jump to infinity. So understand the intuition. You don't need to understand the detailed math too much. So that means what? Originally, I have this function. Now I have this. And this jump to infinity, right? So I have a point here, and then suddenly jump to infinity. And this is infinity. So I change from here to here. I don't allow red to occur. And this funny thing is called indicator function. If x is inside a set A, then I do nothing. Value is 0. If x is outside my A, I send everything to infinity. Go back to this example. If my x is in my yellow region, will I send everybody upward? No. So I keep my black thing. So you can think of, this is my f. This is what? This is f plus indicator. And since in this part, indicator is 0, so I have f plus 0, which means f. But this part, I have f plus infinity. Then I have infinity. So that's the idea. So in this sense, the idea is, now anything x inside set A, this is constraint. I have constraint. This is the constraint. Now I don't have any constraint. I don't want to have a subset here. And I just put this here. And this function will deal with the constraint because for any body that violates the constraint, I just send it to infinity. And since I want minimization, what's minimization? Minimization is going down. What is infinity? Infinity is the biggest value you can get. So that means if I minimize this, I must not touch the biggest value. I must go down. Then when I go down, by this definition, I must stay here. So this is how you deal with constraint. And this is a singular function. What does it mean? Because this function you cannot differentiate. It's some real function, but this will become very useful. So this is just formality. This is called indicator function. Okay, but then we have also another tool. First, I have an indicator function. It's like this. So what the indicator function is basically saying is A violated. So let's say A is some logic condition. If A is violated, then go to infinity. If A is true, then 0. Then there is the opposite. This is asking, is A violated, right? Then the opposite is A true, and this is called characteristic function. So what the heck? If A is true is 1, A is false is 0. Yeah, that's it. So you can think of it as an on-off switch. And then we also have two more. The first is absolute value, okay? And then you have max. Max is what? Max is AB. If A is larger, output A is B larger, then output B. And you can actually write down max as absolute value is A plus B plus the absolute value divided by 2. You can draw the picture, but I don't want to draw it anyway. Now, lastly, we have the clip or non-negative projection. So what the heck is this? Basically, is anything that is larger than 0, then you keep it. Anything that's smaller than 0, you replace by 0. This is 0. So after 0, you keep it. Before 0, everything is 0. And you have a point here. Okay,